thought after my recent video about LDR potential dividers we should have some fun and actually implement a real project. Before we start, let me just highlight the purpose of my build yourself project videos. They're designed to be exactly that, straightforward projects that can be built on breadboard using cheap and readily available components that you can experiment with at home. Please leave comments below detailing your additions or adaptations of the projects. Every so often I'll release a build-yourself project that will contain sub-circuits, which I've already released during video tutorials, such as those in my basic building blocks playlist. Today we're going to build an optical counter. It consists simply of a light beam, a counter, and a single 7-segment display to show us our current count. This type of circuit was quite popular when I was a child if you had scale electrics, because you could use it to build your own lap counter. Those that are more competitive also adapted it to trigger timers and so forth, so you could time your laps and challenge your friends. However, this type of circuit is more widely used, for example, by theme parks counting guests in and out, or maybe at the gate of a ride to see how popular it is compared to other rides. That may use an infrared source rather than LED. You can't use a physical switch for this, as you want people passing by to trigger it, or a car pass under a gantry for the scale electrics. There are lots of uses of this circuit, and at the end of the video I extend the project and create a rotation counter. We've already discussed the LDR potential dividers. I'll link that in my video below in case you haven't seen it. Let's jump straight in by looking at our counter chipset, which I've chosen to be the 4026B, simply because it's a one-chip solution consisting of a counter and a 7-segment decoder. Taking a look at the datasheet, let's have a quick read through it and familiarise ourselves with the circuit diagram and chipset. So, the 4026 consists of a 5-stage Johnson decade counter. The decade counter means it counts to 10, but in electronics it is normally considered that 0 is the first count, so it'll actually count from 0 to 9. Looking at the circuit diagram, we can identify the Johnson counter at the top left, consisting of 5 flip-flops, which are wired with the same clock and their outputs connecting to the adjacent inputs. These are now configured as a shift register. If we interpret the outputs, we get the following truth table. As you can see, the Johnson counter is not a binary counter. It basically works by filling the flip-flops with 1s until the register overflows, and then it refills with 0s, then fills back with 1s, then fills with 0s, and so forth. Because the last flip-flop is fed back into the first flip-flop, it will continually count round in a circle. This is often referred to as a ring counter. Back to the text, it says an output encoder converts the Johnson codes to a 7-segment decoded output. We can see that this logic gate arrangement here performs that task, as well as including the display enable. So to display enable has to be high for these logic gates to pass through the 7-seg combination. Reading on, it mentions low package count, etc, etc, etc. It also mentions the clock input, reset, clock inhibit, common outputs such as carry out, so that allows you to chain several chipsets together to cascade them to create a bigger counter. It also says there is an ungated C segment. So ungated just means that isn't dependent on display enable, so that will be a separate output that allows you obviously to do the counter dividers. A high reset signal clears the decade counter to its 0 count, fairly obvious. The counter is advanced by 1 count at the positive clock signal transition. That's important, so that's going to be a rising edge clock. If the clock inhibit signal is low, so obviously the clock inhibit can't be high, otherwise it will inhibit the clock. Counter advancement via the clock line is inhibited when the clock inhibit signal is high, fairly obvious. The clock inhibit signal can be used as a negative edge clock if the clock line is held high. Anti-lock gating is provided by the Johnson counter. Okay, so anti-lock gating, that's quite interesting. That basically means they've added extra logic gates to prevent the counter going to an illegal state. So this can happen due to power cycles or problems with resetting, etc. So an illegal state could be, for example, like a 1 surrounded by 2 zeros. That shouldn't happen. Okay, just reading on a little bit more. After the anti-lock gating, obviously that's to ensure a counting sequence. The carry out signal completes 1 every cycle, every 10 clock input cycles. Yes, that's fairly obvious. It's in a decade. Is representing the decimal numbers from 0 to 9. Yes, as I said about it, that 1 starts from 0 rather than 1. The segment output 7 segments go high on the selection side. If the display enable is high. Yeah, so that's all fairly common and straightforward. So if we just have a bit more look at the circuit diagram, we can also see some more important things, such as the clock inputs. The clock input we need has a Schmitt trigger on it. that is very important for us because we're going to use the LDR potential divider to drive the clock input, and you cannot put an analog output into a digital input. It's not given a high or low signal, it is merely given a reference voltage, and this chip has to interpret that as a high or low pulse, and usually that means, for example, that it will interpret something over, say, 4.5 volts as a 1 and less than 0.5 volts or 1 volt as a 0. You'll find later in the datasheet, I'm sure it'll tell you it's Schmitt thresholds, it will probably be called. And we'll look at those as well, because the Schmitt trigger is very important. We'll look at that in detail a bit later in the video. If the chipset itself didn't have a Schmitt trigger, we would have to add one to use our LDR with it. Having a quick look, other things around, is there something else we can talk about? Yeah, we can talk about the outputs. Can we see that they all have buffers? That is usually for impedance and noise lowering generally. You'll also notice that the little bubbles, can you see the bubbles, so it's sometimes called, either side the gates? That just basically means it's an inversion of the signal, or the gate, the object itself is inverting the signal. So if the bubble is before the gate, then it's showing that that's an inversion of the signal coming in. If the bubble's after the gate, then it's showing the gate is doing the inversion. So that can be quite interesting. So if you look at all these AND gates, for example, a lot of the signals coming in have been inverted, and a lot of this is to do with the way that the FETs and that are actually put into the chipset. Another common question that is often asked by hobbyists and beginners alike is the power agents for these chips. If we look, we have two power rails on this chip, one that says VDD and one that says VSS. And it's not that common to see V plus and ground on these chips, and this stems from the way they're made up, the FETs they're made from. So a FET, for example, has a drain and a source, and usually the drains are connected to VDD and the sources are connected to VSS. So the drains will be connected to your positive rail and the sources will be connected to your ground rail. Now, this doesn't actually mean all the drains and all the sources inside the chipset are connected to the positive rail or to the 0 volt rail if it's all the sources, etc. This is just a way that they tell people how to wire the chipset up. It's not an overall rule. And you'll notice if you look at old transistors chips, you'll find they have VCC or VEE. VCC is the collector and VEE is the emitter. So the idea being the collector goes to the positive rail and the emitter goes to the ground rail. And again, that's the same thing. Now let's have a little look at our Schmitt. So let's have a bit more of a look at our Schmitt trigger. So we can see that when we pass through our light beam, we get a rising edge and the counter counts on. And you see it in the back on the scope. But the thing is about the Schmitt trigger is it creates two thresholds. So you've got to be over a certain voltage for it to trigger as a 1, and you've got to be below a certain voltage for it to trigger as a 0. If I just turn my cursors on, I have already configured them. So in the datasheet, it says a input low has to be below 1.5 volts and input high has to be above 3.5 volts. So we can see that on the scope here. If I now run my thumb across it, you can see we're going to travel through the thresholds to get it to count on first. So we've got the 1.5 at the bottom and the 3.5 at the top. Now it has to be done orderly, so to make a high it has to go from below 1.5 to above 3.5. So like so. The counter's moved on. If I now let it ease back a bit into between those values, like so, you can see that if I now go high again, it doesn't count. So it's got to go low fully before it will re-trigger as a high. So go all the way low, now go back all the way high, and it counts as a 5. This means our rise time and our fall time can effectively be unlimited. A proper digital chipset, it will have a strict timing regulation where it will say you have to go from low to high within so many nanoseconds, for example, for it to be an actual proper signal. And if you go beyond that, so if you go outside that time limit, then the chipset will behave erratically, and they'll warn you about that in the documentation of the chipset in the datasheet. So let's just, for example, have a little go to see if we can find out if these thresholds are actually proper. And we can trigger. So I'm going to very slowly try and. Oh yeah, did you see it? It actually went then. So go back low again, come back high. Yeah, count it again. So we can see that top one actually can move down a bit to the top of that peak there. So let's try again. Yeah. And again. So yeah, so it's actually a bit below 3.5. So let's see if we can do exactly the same for the bottom cursor. Let's see if we can change to the bottom cursor. And let's see if we can now go up. Do we trigger? Yeah, it's triggered. And now we're going to keep going down a little bit and go up again. Not quite there. Down a little bit. No, it's okay. Yes, so we can see actually we can move our cursor up a little bit because it counted then. So we can now see that they're the actual triggers. So that's about 3.16 and 3.17. Interesting. So the actual thresholds differ slightly from the datasheet, which is quite interesting. Right, something else that's interesting to notice is going back to the rise time and the fall times. So these can be unlimited, as I mentioned earlier, and even the datasheet says that. So that's quite key, and there's the Schmitt trigger that helps us there. And the fact is we don't have to go straight from high to low. We can sort of go between the two and edge backwards and forwards, and it won't make any difference to the chipset. So that again is the Schmitt trigger that really helps us there. We couldn't do that if we didn't have the Schmitt trigger. Let's have a quick look at our circuit diagram for completeness. So we have our white LED going towards our LDR. Our white LED has a current limiting resistor of 100R. I've worked it out simply by Ohm's law. So R equals V over I. We know the forward voltage of a white LED is 3.1 volts, so that's 5 minus 3.1 divided by 20 milliamps gives us 100R. The 1K resistor on the LDR gives us the best voltage swing, so that's why I've chosen 1K there. Again, if you look at my potential dividers with LDR video, you'll figure out what that resistor can do by changing that value. And I've decided 1K is the best for us. And that goes to the clock input of our 4026B, which of course is a Schmitt input. It is not an ordinary logic input. That's important. We also have clock inhibit and reset held low, so it enables our counter. We have display enable input high, so that it will show us the count number. We have display enable out, carry out, and ungated C all left unconnected, which is fine. We don't want to connect any outputs to ground. That'd be silly. We want to leave them to float, fine floating. It's the inputs of a chipset you want to make sure we know the state of. So if we've got an unused input, we probably want to tie that to ground, but outputs can stay as they are. So that's fine. And as you say, we've got VDD connected to 5 volts, VSS connected to ground. Then we've got our A to G connected to our 7 segment. So bear in mind that the C segment actually has both ungated C output and a C output. So we want to make sure we put the C output to the 7 seg and then leave the ungated C unconnected. Then we have a 330R resistor connecting our common cathode to ground. Now, I've just put the 1-dropper resistor on the common cathode display. This might attract some criticism, as it is common belief you have to put 1 dropper per segment on the lines into the display. Using 1 dropper on the cathode is fine if you make sure that and you work out the max current through the segments is not maxing itself out. So you want to make sure that you work it out on the lowest number of segments lit, which would be a digit 1, because only 2 segments are lit for that. So when you work out your dropper resistor, work it out on 2 segments, so effectively 2 LEDs. But we have to be careful here. We're not working the max current out for our common cathode via the LEDs in the common cathode display datasheet, we want to look at the datasheet on the 4026B and see how much current it can source per output and work it out on that. So in this case, the datasheet says 4 milliamps at 5 volts. So we have our 7 segment, which will be 5 minus 2.5 volts divided by 8 milliamps. So why 8 milliamps, not 4? Because we've got 2 segments lit by default, which is the digit 1. So in which case we get 312.5 R, so 330 R is fine for us. So there you have it, a simple lap counter. I highly recommend building one yourself. And why not extend the project? Use 2 4026s and have a double digit lap counter maybe. Have 10 7 segments. Who knows? Try it, see what happens. Maybe change it for a switch rather than an LDR. Or maybe a reed. Maybe make it magnetically operated. There are loads of ways within this project. In fact, here is one. I've altered the LDR divider by swapping the power connections around. This is because I now want it to trigger when lit rather than when dark. I've attached a cardboard disc on the front of a hobby motor and placed it in between the LED and LDR. Using a speed controller, I will vary the motor's speed and the circuit will count the motor's rotations. This is not perfect, as the faster the motor spins, the less responsive the LDR will become due to the average light level increasing, as you can see the moment the counter stops in my footage, which highlights this. However, it's just another idea for you. Hope you've enjoyed the video. If you have, please give it a big thumbs up. And until next time, keep experimenting.